you guys, thanks for having me. Start a stopwatch. Hi, welcome to my presentation, Beyond the State Machine. Is there better options than a state machine? Controversial, I guess. My name's Tim Streeter. I'm a senior systems integrator for Software Systems. I'm originally from New Zealand, but now based in Melbourne. I've been working with LabVIEW since LabVIEW version 5, I think. That was about 1999, about 26 years ago. I'm a certified LabVIEW architect, certified lab tester and developer, and I'm a big fan of object-oriented programming. I used to work at a small rocket company in New Zealand. My job was writing control logic for parts of the launch system, but it's quite a complicated job. I started on the code, working with the usual suspects, trying to work out where the best way to go, but I got pretty buried very quickly. I got buried in the complexity. In frustration, I Googled, what is better than a state machine? And it turns out it was behavior trees. My reaction was, but what is a behavior tree? So, of course, I went back to Google. A behavior tree is a type of a directed decision tree used for modeling control logic. Execution starts at the root. Will I go on the screen? No. Execution starts at the root, follows structured rules to traverse child nodes, and BTs are typically used in robotics, AI, automation, to implement hierarchical top-down control, as well as gaming, actually, as well. The example of this is a typical gaming type behavior tree. It doesn't seem very useful for us. So what does searching in drawers and cupboards got to do with LabVIEW? So let's have a look what LabVIEW does. What I can do here's a more relevant example, I should say. This is a simple test sequencer. It pretty much is going to waiting for a start event, runs through a series of tests. If all tests succeeds, it passes. If any fail, it fails. But then this is a tree. What are the rules? So let's go to some basic terminology. Each block in a behavior tree is called a node. The parent nodes are positioned above it. Can I actually icon over? Oh, there you go. So the ones that are above it are called parents. The ones below it are called children. Each node can return one of three resulting states. They can any one can return a succeed, a failure, or running. There are three basic types of nodes: composites, decorators, and leaves. First, let's go over each. Let's get to composites. A composite node has one parent and multiple children. A composite node controls the flow of logic and behavior by managing their child nodes. There are three main types. There's the sequencer, which steps through the children until one of them fails. There's a selector, which steps through the children until one of them succeeds. And then there's parallel, which runs them simultaneously. Next, we've got decorators, one parent with one child. Decorators used to modify or control the behaviors of a single child node. They just how results are interpreted or how often they're repeated. We commonly use decorators are repeaters, which repeat until they meet a certain condition, a succeeder, which forces a succeed state, failure, which forces a failure state, and notting, which just inverts state. I mean, pretty straightforward stuff, really. Then we have the leaves. These are the ones that do stuff. One parent and no children. Leaf nodes are the endpoints of the tree. They perform the actions or evaluate conditions. These are some typical examples. You got logging messages, waiting to pause the execution, testing on specific values, and assigning values from one variable to another. So now that we know a little bit about what each of these things do, we can go have a look at what this tree does now. We got the repeater at the top. It's like this one's set to run forever, so it's never going to stop. Then it's going to call the sequencer. It's going to try and run through this sequence from beginning to the end. It's going to wait for start is only going to return success once it's got start. So it's going to repeat this branch over and over again until start happens. Then it'll go to this stage, which is going to step through these steps until something fails. In this case, we got it's then this. We're going to run the sequencer. It's going to run through the steps: test 1, test 2, test 3. If they all succeed, it pass. But if anyone fails, it's going to follow this bunch around and go to fail and run the fail state. Just a quick overview. Okay. But what does this look like in LabVIEW? This is what the actual behavior tree will look like in LabVIEW. As you can see, it mirrors it. It's simply rotated by 90 degrees. So you have to have the code with your head at a funny angle to trying to get that to so it looks the same. I did rotate it at one point, but I left it out. One key advantage versus other behavior trees versus implementation in other languages, this is actually what the code looks like, unlike others that require an editor. There's Python versions of behavior tree editors, of behavior trees which require an editor. There's Java, C++. All these behavior tree languages need their own editor, but not in LabVIEW. Okay, let's start with my simple test script. I did 3 versions of different levels of complexity. Let's have a look at this. This one here. Okay, simple LabVIEW VI for paneling. And this is the main level code. This where I've got and here is my behavior tree. And there it is, just like in the slide. Thanks. And I'll show you it running. It's actually a simple test sequencer, so it's actually going to display the log message here. We're going to see some generated waveforms, some generated voltage, some simulated stuff, and it's going to run through a test, indicate pass-fail status. Let's run it and see how it goes. And start a test. We get a pass, fails, so on and so forth. Cool. The messages are actually just, these are actual branches. I think I forgot to mention that a subsequence is, a subtree is called branch. So these are bits you code that are made of another behavior tree's behavior. And it pretty much follows the same idea. It's actually just going to run this comparison. So we grabs a value, tests it, and then logs a pass message. If not, logs a fail message. And that is a test sequencer. I think I'm moving quite quickly, actually. And yeah, and this is sort of a top level VI. So I have this is the behavior tree. It gets past the execution engine, which then starts execution. And this here just mainly this in loop is just updating the front panel. It's just polled. And once finished, hit stop. It just runs the top and closes. There's an actor there somewhere. I don't put them front and center for everybody to see though. They're just part of the API. Just a little dig anyway. I'm hesitant. Any questions at this point? I know you're supposed to put them at the end. Okay, I have another demo. This is a that one way. This is a car wash. It's actually a comes from the NI CLD exam prep material. They have a solution for one of their exam questions for doing a car wash. So they give you the front panel, and then you fill out. And this is the solution. The solution is a state machine. The main reasons I don't like state machines. They're hiding everything. You've got to go through everything to figure out what it's doing, and you've got to trace it. It's not in front of you. LabVIEW I like because everything that is in front of you, you can see what that is trying to do. But when it's hidden by in a whole bunch of different cases, maybe they're named, but you sort of got to go through them. And that's why I liked a behavior tree. So I did I built this again using on the right. Here we go. Right, so I did the same thing. I should actually show it running. Here we go. So its idea is that you choose what you want it to do, whatever, hit start, and then you simulate your car moving, and it runs through a series of cleaning things. And then you move to the next station, it runs the next set of cleaning things. So this would be a, and here's my version. I had to add a log message on there because that highlights what's going on. It's the same, does the same things, moves to station 1, except I've got moves to stage, so on and so forth. So that's the same thing as that state machine, except, I mean, it's not the most complicated state machine. It's not the worst I've seen. But some of the state machines are pretty complicated. But this is what I created. This is, I think, a lot simpler. It's pretty much waiting for you, updates, clears the wash indicators, sends a message to say your washing started, waits for a start button, and then runs through each of these, they're branches, but they're all pretty much, the name of the branch tells you what it's trying to do, which is just generally good program. So you actually, this one here is going to be doing the car entered, so that's waiting for the car to enter. It's not very interesting. Then this is what we're going to do at station 1. So it's actually just going to run a check, make sure that it waits until we're at station 1. When we're at station 1, we're going to set the variable to clear the, sorry, I can't read my own, that green and white. Clears the status for that, starts doing the wash, starts doing the bug remover, and then sets the state to move on to the next router position again. And then it's hierarchical, so it can keep going down. Pretty much this one actually is just running the same behavior with different messages. But you can keep digging, making this, if I wanted to actually put in the code for actually doing more of the valve control, the IO control, then I can actually just keep growing at, you know, like what does a, what do I call this one? This is the, I just reuse the same code for each thing because I wasn't planning to do an in-depth thing. But if this was like station 1, I'm doing the bug wash, I could, you know, set up all the valves. That could be done at this level. I set this valve, wait a bit, set this valve. Once the pressure's done this, then you do that. All that sort of logic could be done without actually writing any more LabVIEW code. It just sort of like a, yeah.
2 seconds, Nancy.
But the behavior, oh, sorry, the behavior VI with the arrow, can you open that one? The one that's after, there you go.
That one there?
Yeah.
The sequencer.
Yep. Can you, yeah, just open that.
Open it. What does it look?
Yeah. There you go.
It's just declaring, it's a class, and I'm just passing in the nodes into the class, returns a class. That's, what's crazy is the simplicity of the code. I'll show you that the repeater is even crazily simple. I'll even show you one if you're interested. I guess if you got any questions, I guess this is it. Yeah.
So the order of the elements in the array determines the execution control, right?
Yeah, it starts from left and goes to right through this.
But
the bottom.
Like your sequencer goes through the elements in the array in order, right?
Yes, in order.
So if you want to programmatically change, you know, say there's conditional logic, and so you change the execution order of the sequence, that suggests that Do you send a message to do that, or you change does everybody have permission to modify the array directly?
Do you mean just change the order, like I can move the order around?
Yeah, but programmatically. Yeah, I get statically. That makes sense to me. It's like if you want something that happens in a sequence to change what happens downstream, does that then just suggest that the code modifies the array directly?
No, the array hasn't changed.
Okay.
Everything's mostly statically allocated. I have got other methods for adding events into here and queues, so you can queue in different variables to make more dynamic things. But pretty much the idea is that if this steps through, and then it will just return from this state out, and then back in again.
So say for example, just to say in a hypothetical, I'm testing a battery, right? And so I'm charging it, I'm discharging it, I'm charging it, and then I'm doing spectroscopy or something. But there's conditional logic that says, hey, if there's a fire, you should trigger an alarm and start a sprinkler, right? Like just making something up.
Yeah.
Like, would that then alter the sequence behavior? Do you change the array and say, oh, I got to trigger the sprinkler now?
So I have built a battery charge using this. So you'd have a loop that would be doing something. Okay. This is where it's a little bit clunky. You'd have a loop that would be doing something. And in that loop, you'd be checking the status of your alarms or any other conditions like that. That loop would be choosing to finish on fail or succeed. So probably finish on fail, like while everything's going good, you'd probably make it true.
Okay.
And then it's repeating and repeating until something fails. Like, is it finished? You'd probably then have to run. You'd probably then have other conditions and alarms and checks after that, like has something failed while you're doing something. I've only got the two actual succeed or fails inside a loop. So if you're continually in a loop and you're continually, say, like inside, let me dig down into one of these, the underbody wash. It's actually, if I'd had in this loop and I'd have a repeater in here, and it was, instead of just waiting for so many milliseconds, I'd be continually doing something. So I'd be in a repeater here, and if something happened, I would check, cause that's a repeater to stop. It will return fail to the outside, and then you'd have a fallback, or a selectors use a fallback. You'd have a if fail, then do this thing situation. And then you'd look after that fail condition, go through all the different, was it this, this, and this, and then perform something accordingly. But you'd actually because it'd be, if you've distributed your actions throughout a place, you'd probably want that code all over the place. So you'd probably make up another branch with it in it, or alternatively set up a parallel loop, which would be monitoring stuff and doing stuff. And then maybe you'd still inside your control loop, you'd have to monitor status. I mean, I've tried all those things. I think
sounds like there's a lot of different ways to do it.
Yeah.
And one other quick question. So in the behavior tree, the leaves, as it were, in your tree, you can have multiple leaves running at the same time?
That's what the parallel is for.
Okay.
I have a multi-threaded parallel. I did not point that one up. There's this parallel. There's where's my toolkit? This is my, the bit that I haven't got to in the slide was that this is open source. It's free on VI Package Manager, and if you search for Tim Streeter on GitHub, you'll see my open source repository. Composites. The threaded parallel, it actually looks just the same as all the others, except all the nodes are actually allocated a separate thread and then run in their own hidden actor to actually do the code. It's the same actor that runs the whole engine, so the whole thing's kind of, so then if you have some code, you could start up and run one code to do one thing, another code to do the other thing. There is message queuing between them if necessary, but stuff that was really safety dependent, I didn't want to use queuing. I mean, in queues and notifications, everything was statically defined. so that every possible combination was already allocated an outcome. So I could actually do something, and if there was a possible fail option, there was something I had to put in there to fail it, to do on fail. So if this failed, if batteries got too hot, we do this situation. If this did that, we do that. If we're doing this, there was the battery charge system I was talking about was for Rocket Lab, and it was the batteries are charged in situ in Rocket, and were carefully limited to many, many different things, so they couldn't be destroyed because you had to take the batteries out and delay rocket launches. But yeah, and also it's nice and simple. The code's simple. I was going to show you what a repeater looks like. It's like the most, even though it sounds like you actually should be putting this inside an actor. Getting too many VIs up on the screen. I'll show you what's inside a repeater. So it's really, each one's just a class. As an X, and that's the code. It just looks at the state indices. All it does when it's repeating is just set the status to running, and that's all. Running until it meets finish on certain conditions, succeed, fail, and this is just the status of the previous steps. Yeah, and is any other questions? Yeah.
Do you want to ask yours, Kristen?
Thanks, Tim. So have you used this for actual deployed applications in industry?
Yeah, I developed this at Rocket Lab for not this code because I couldn't take it away. I actually rewrote all this code. I made it better, but I used this approach at Rocket Lab for the launch tower and also for the battery charge rig for the rocket. It was designed to be simple to code the VIs, that the simple, clean code, and most of it you don't need to do. Most of it it's actually, and also that it's hard to introduce a bug when it's so obvious in front of you, which is my sort of my thing is keeping the code simple. And this, yeah, and they use this in gamers and stuff like that. This approach, you can get the people talking about behavior trees in different forums, robotics. I learned it from the gamers, the approach, and worked out how to do it in LabVIEW. Yeah.
Tim, can you talk us through a little bit on that genesis story of this? So you mentioned you didn't like state machines. You Googled alternatives and
Yes.
then basically decided to start your own framework. But you then mentioned you liked object-oriented programming. Did you look at other frameworks like Actor Framework or anything, or why did you then pretty much build it yourself?
It's not, I wouldn't call it a framework. There isn't a tool that creates this code. I mean, you have to go and, I have libraries that you can build this together and plenty of examples, but there isn't a tool that goes, oh, here's create this for you. But you can start from the examples, pretty much that's what I do.
Did you look at other frameworks and they weren't what you were after, or?
Well, I did. That's what I did say, that I kind of used to look at the usual suspects. I mean, I pretty much started with the state machine. It's not a framework issue. It's like a logic issue. Like a framework still, the Actor framework still needs some logic, decision logic, and that had to be done in if it's a consumer producer, like the consumer side had to perform some logic based on its variables. But when the logic and your state machine to handle that logic gets really, really complicated. I mean, once you've seen a state machine beyond 20 cases, it starts getting horrendous, and then you come back to it later and now how does this go unless you've diagrammed it correctly? I've had nightmares, complicated systems that were really not that complicated, that were just horrible to edit and control, and trying to reorder stuff. Like and in this behavior tree, I can change the order of the sequence trivially. Like if I wanted to have this happen before that, then I just swap those two wires over.
Because what I like when I'm looking at this, what I like is there's not extra infrastructure code that is cluttering the block diagram.
Yeah.
It's like sensory overload on some applications where it's like there's so much going on. It's like, okay, now where do I need to go? It's just clean and crisp.
Thank you.
I understand the philosophy to go down that path.
I mean, you can make it messy looking. I have from experience of what makes it looking tidy. This is my approach, everything up to the top level. And then you break it into known stuff that makes it look complicated. You then break it into actions that you want it to do. So then if I made all these branches into the top level there, then it'll just be one big, huge mess, but you still get into trouble. But yeah, I can modularize it, make it nice and clean and tidy and easy to understand. And I mean, once you know how a behavior tree works, do you really need much documentation on it at all?
When I'm thinking about kids that are getting started and they're doing their first applications and keeping things really, really simple, it's easy to read.
Sorry?
I said it's easy to read for somebody getting started and doing some of their first applications.
There's courses on behavior trees online. So they used an Unreal Engine. PyTrees uses it for robotics. There's plenty of stuff on how to use it. And then of course you just grab some examples and play with them. There's usual one at the top of this, always the one that runs first. So if you ever, one mistake I used to do a lot was I'd put a weight. If I needed a weight so that it slows things down a bit, if I put it anywhere else except for a beginning, it would never get run because it never made it to that point. And so that's a little errors I used to do. So if you want something to wait, I'd put it at the beginning because then it would always run first and then it would always be a wait. Which actually brings me to one of the decisions over other behavior trees. A lot of them deal with ticks. I didn't want to deal with a tick because it would actually tick through each of these things. And by the time you get through it, you've waited, extend the time to action, where I've removed ticks and it added waits. So you can actually get quickly to the bit you want, wait, so you're not using up all your CPU, and then, like inside your repeat loops and stuff like that. To make it fast when you need it to be fast and slow it down when you don't need it to be.
Quick question on documentation-wise, because obviously it's got a good look to it. Have you thought about having an automatic documenting tool that goes through and sort of staples everything together so it builds up your full program behavior tree?
Yeah, I don't really, it's an open source project that's just me. I don't really have time for nice luxuries. I mean, I could use a LabVIEW print screen, generate the LabVIEW thing from it, and there you got a code for that. And then one for each one of these.
Yeah, nice.
You could run the anti-doc tool. The anti-doc was mentioned by Fab yesterday. And it was designed for DQMH, but it'll document classes as well now. It'll lay out all the UMLs and everything.
Yeah.
So anti-doc on VIPM.
UML diagrams and things. So if you had a tool that could go in and sort of see when it's doing a parallel structure, etc., and then build up a diagram from that using the LabVIEW block diagrams, that would be really cool. But yeah, we'll see if we can give you some time.
I mean,
Stuart saying Nigel could do it in Q3.
I mean, I would argue that that's enough. If you know where it is, I usually make, in my code format, this is my typical structure. Initiate IO, do something, initiate everything, then start execute. And then wait till to finish, then stop.
Are there any other questions in the room?
I've got one, Tim. Can you just show us the palette, please?
Yeah, I did have that in the presentation. I removed it, thinking I was going to take too long. So here's my palette. I have my composites here. Parallel, multi-threaded parallel, which is actually interleaved, by the way. It will actually interleave the steps. So as you step along the different child, it would move backwards and forward. So then there's selector and sequencer, decorators, not, repeat until timeout, repeater, failure, succeed. I mean, there's not a huge a lot. My leaves, assign value, test abstracted Boolean, wait, log, and then my synchronous, center notifier, wait on notifier, center queue, wait on queue.
And then the doing stuff, is that then VIs that sit below that?
The GUI stuff.
The doing, whereas the actual
yeah.
actions, the test steps. for
That's something
instance.
else. This is my another thing that I could have talked about, which is my abstraction layer. The one thing when I did this at Rocket Lab, one thing I had problems with was we changed hardware. Originally, I created this system. Each leaf had a did actual. I'd have a test of value, test of string, test of this, and test of that, and then if it's greater and equal and all that, and then they changed it, and I was directly testing that IO, and then they changed it all, and I'm going to have to write this all over again. So I created an abstraction layer. So this is that abstracted out the hardware, and that pretty much what you see is my abstraction layer VIs. This is actually writing to abstracted Boolean, reading from extracted Booleans, and that's another complete different extract class, and a polymorphic too.
So is that a dependency of it, or is that you're just using that in conjunction with it?
The abstract types are a dependency.
Yep.
But the base abstract type has very little in it. It's mainly just empty parents. The idea is that you would choose something like the omnibus or the behavior tree does come with its own blackboard, which is another abstraction layer that which is a built-in way of handling variables. Typically, most behavior trees have a blackboard. I think I'm using blackboards here. And this is allocating, yeah, I think they're all, oh no, this is on the bus, where each IO is given a name. And then I tidy it up by pushing it to a cluster, but you could actually directly access the by name rather than by reference. But that wasn't, I kind of wanted to hide that away because that's not what the presentation was meant to be about. The idea is yeah.
So what do you do? Do you just go to your GitHub and or go to VIPM? Is it on
VIPM? I did have a slide for it, but
yeah.
And search for me. TSA. It's I needed a company name. It's just Tim Streeter, Time Space Authority. Tim Street Automation, but it's just me.
Oh yeah, the Americans.
The TSA is the security line at the
Oh yeah,
airplanes.
oh yeah, that too. Pat downs are free. Yeah.
Any other questions?
Yeah.
No. Well, Tim, thank you very much.
No problem.